Hi everybody, welcome back to Chem 163. It is Wednesday, and what does that mean? I don't know, other than it's Wednesday. What are we going to do today? It's chapter 14. We're going to talk about acids and bases today. There is a quiz for chapter 13, and that is due Friday, on the same day as lab worksheet number 1. Regarding the lab, a bunch of students have been asking me questions about lab worksheet number 1, and that is great. Please continue to do so. What I want to avoid is that everybody asks me questions on Thursday or Friday night, because I can't guarantee that I will be available on those nights for, like, as early as students would probably want me to be. Like, I'll be available later in the evening. I just have things those evenings. So if I get back to you at 11 p.m. on Friday, that could be problematic if you're trying to turn it in on time. So get any questions to me as early as possible to maximize the chance that I can help you, because I'm happy to help you. I just do stuff on Thursdays and Friday nights, and if you get a late response from me, that is why. Let's see, what else can we talk about? Lab number 2 on Friday. Please make sure you look through all the pre-lab stuff, because the pre-lab is due before that lab starts. Lab number 2 involves calculations that are... I feel like lab number 2 is probably the hardest calculation lab in the quarter. So please read through it very carefully. You're going to be doing 2 titrations, one of an organic solution containing iodine, and one of an aqueous solution containing iodine/triiodide. And the titration is something that you did in 161 for the wine lab. We're going to do, it's the same reaction, thiosulfate and iodine, but the I wanted to call it the situation, I guess, that the reaction is in is unique, because we have 2 very distinct layers. And we'll show that in the class when we discuss it. There's really not much I can say other than just showing it to you, because seeing the dichloromethane and water mixture together, like, you can visualize it, and there's a picture. But doing the reaction is probably the best teacher, so we're going to do that on Friday. So make sure to arrive on time for lab on Friday. All right, so for today's lecture, we're going to talk more about acids and bases. So we defined acids and bases at the end of the last lecture. We're going to formally define them in terms of their chemical formula today. There are 3 definitions of acids and bases, and we're going to explore all of them. So the first one's the Arrhenius definition, and this is by far the worst. However, it is helpful for just looking at a formula going, aha, that's a base, or aha, that's an acid. The other 2 are a little more thought involved, but are more complete definitions. So we're going to rely on Bronsted-Lowry the most. Lewis is also an excellent definition of acids and bases. We're just not going to use it all that much. And then the Arrhenius definition is our very, like, surface level definition. And you'll see what I mean by that in just a second here. So the Arrhenius definition of acids and bases are based on the formula, and these are the qualities that we're looking for in either an acid or base. So if you are an Arrhenius acid, then what you do is you dissociate into pieces. One of those pieces is H+. So for example, if I had HCl, it would dissociate into 2 pieces, one of which is H+, and we don't really care about the other part. There's the acid part right there. Now, an Arrhenius base does the same thing, except, oh my goodness. Hi. Hi. Do you have to do this right now? I don't know if you could hear Maya. She snuck up on me somehow. So an Arrhenius base does the same thing, but one of the pieces that it dissociates into is hydroxide. And so an example of that would be sodium hydroxide. I didn't put my AQ here, but that's okay. And there's my base. Oh, and now Maya's gone. I don't understand this cat. She got right up in my ear and meowed at me. I don't know if you could have heard it in the mic, but it startled the shit out of me. And Maya's like the gentlest cat. Like she doesn't have a mean bone in her body. All right. So there's our definitions. We're going to be looking for H plus and OH minus. That's our goal. Now, H plus is literally just a proton. Because hydrogen would be one proton and one electron, and if I make it positively charged, it's just the proton. Protons are real tiny, and they're positively charged. Anything that is small and very charged is going to attract things that are oppositely charged to it. Since water has a polar component to it, and the negatively charged polar component of water is the oxygen side of water, water is attracted to these protons. And the end result is that water will collect the H plus to form this. And this is called hydronium. Hydronium is what we suspect the mechanism by which H plus is carted around through solution. It doesn't stick around on its H plus doesn't stick around on its own. It's just too charged. Now, whether there's one water molecule or two or three that hydrate the H plus, it's very difficult to say, and I think that research is ongoing for that. But for our purposes, whenever you see H3O plus or H plus, the intent is the same thing. Because we really don't care about the water part of H3O+. We care about the acid part of H3O+, which is the extra H plus proton that's being carted around. So depending on the source that you are looking at and whether the scientist really cares about abbreviating shit or not, you might see H plus. H3O+ is probably the more correct of the two, but the intent is that they're the same thing. All right. There's my base. This is a base dissociating water. All Arrhenius bases are ionic compounds, so it's very easy to have these things dissociate if your solvent is water. Now, we don't always do acid-base chemistry in water. In organic chemistry, you're going to do acid-base chemistry in all sorts of different media, and so it's a lot less soluble. But those substances are typically have different properties to them, and you're not necessarily going to be dropping sodium hydroxide in there, although you will for some reactions. Now, a feature of acids and bases is that they neutralize each other. If I combine the two components of acids and bases together, you create water. Now, interestingly, the word neutral is used to describe the product of an acid-base reaction, because we have neutralized the acid and the base. And so what we're going to do is we're going to call water pH neutral when we get to pH in a little bit here. All right. Now, the Arrhenius definition of bases is, again, great for, like, a first glance at something. You can very quickly tell if something is an acid or a base, whether it contains H plus in the front of the formula or hydroxide somewhere in the formula. But the issue that we run into with the Arrhenius definition of bases is that it doesn't predict all bases. For example, ammonia is basic. If we put a pH strip into a solution containing ammonia, it turns blue. There's no hydroxide in ammonia, though. So how the heck does ammonia fit into these rules? Well, the answer is the Arrhenius definition of rules is incomplete. So we change them. And that's where Bronsted-Lowry comes in. So Bronsted-Lowry is a more complex definition, just slightly. but it is much, much, much more feature complete in determining bases. Acids are actually very easy to determine. They follow the same rule. However, we have written the language a little bit differently. Instead of dissociating into two pieces, one of which is H+, we're going to write it this way. A Bronsted-Lowry acid donates H+ to the solution. So I am an acid, I have H+, here you go, it's yours. I have donated it to the solution. Now, what will a base do? A base will accept it from the solution. I'm a Bronsted-Lowry base, I will react with your H+. So bases, like we said on Monday, neutralize acids. So we're going to use that as our definition. A base is anything that reacts with H+, according to Bronsted-Lowry. Now that's going to incorporate things like this. So if I have ammonia and I react it with hydronium, then I get something like that. And what this means is that because ammonia accepted H+, that makes it the base. All right. Now you could probably see that this is the sort of thing that we're going to be doing, is we're going to be identifying what thing is an acid and what thing is a base. So HCl is very straightforward because, hey, here's this H+. I no longer have it. It's gone. So this must have been my acid. Down here for ammonia, I don't have to necessarily react with an acid. I could react with anything that could potentially give me an H+ here. And so if I take H+ from water, H+ from water means that this is left over. Now, interestingly, that means that we have a basic solution because I have removed H+ from the solution, and in the process, I created hydroxide. In fact, in all aqueous solutions, all bases will do this to some extent. The source of the base, by definition, is always going to be hydroxide. However, if I add something basic, it creates this. Now, whether I remove H pluses from water to create the hydroxide, or I just provide the hydroxide because I'm like, say, a sodium hydroxide base, the result is the same. The solution is basic. All right, so let's look at some reactions and define acids and bases based on our definition. So here, this is pretty straightforward because it's very obvious which thing is the acid and which is the base. But what I want you to do here is, oops, I didn't mean to erase both of these. So I'm going to draw this arrow going backwards too. And what I want you to do is on the left side, assign the term acid or base to either HBr and H2O. And then on the right side, for the reverse reaction, do the same thing. Assign the term acid and base to hydronium and bromide ion. I'm going to give you like 3 minutes to try and type that into the chat, and then we'll go over the answer in just a bit. All right, one more minute. We'll go over the answers. All right. So, since HBr will donate H to the solution, because we could see that it becomes Br minus, that means this is the acid. Now, water has 2 H's, and then after the reaction, it has 3. So it must be receiving the H+, so that makes it the base. Now what we're going to do is we're going to do the reverse process. Okay, if I go in the reverse direction, and I look at Br minus, well, there's no H on it, so this obviously isn't the acid, so this must accept the H+. And you can see that it does, because where there isn't an H on the product side, there is an H on the reactant side. And then this is the acid. For any reaction that is acid-base neutralization, or an acid-base reaction, there's always going to be one acid and one base on each side of the reaction diagram. Let's do another one here. Here's another reaction. I'm going to give you 2 minutes to think about that one, and we'll go over the answer in a second. All right, let's go over the answer here. So the trick to these is really just looking at the two things that are most similar. So here's ammonia and ammonium here. And you can see that before it has 3 hydrogen and after it has 4. So this must have accepted an H+, making it the base. Water here has 2 hydrogen ions on it. Now there's only 1 after, so it must have given 1 away. And then we could do the same thing over here. It's important to note that the reaction status of acid or base is context specific. Excuse me. Because you probably noticed that in this specific instance right here, water acted as an acid. But if I go back over to this reaction, what do we notice about water? Water, you sneaky bastard. It's doing both, right? But it depends on the context of the reaction. Here, water's interacting with an acid, so it's behaving like a base. But in this reaction, water's interacting with a base and thus behaving like an acid. So there's no way to really memorize like what does what, except for certain specific conditions. So, like for example, hydroxide, virtually always going to be a base when you see that. There is one instance where OH minus could be an acid, and it's really, really, really unlikely. And that would be something like this. Where I remove this H plus from hydroxide. This is incredibly unlikely to happen. So you're not going to see that reaction for what it's worth. But technically, as written, hydroxide would be an acid in that case. So again, context specific. Make sure you're looking at the reaction just to verify what it is you're doing, and try not to just commit random things to memory, because the whole point of this is to learn patterns and not just memorize. So, all right. So, because water was capable of doing both things, we assign it a term, and that term is amphoteric. Amphoteric substances are capable of acting as either an acid or a base, but it depends on the context of the reaction. So, turns out there are a lot of amphoteric species out there, because in any context you can probably find a situation where a thing will happen that you don't expect it to. We'll say. Like, you can deprotonate ammonia under the right conditions and make NH2 minus. It's exceptionally hard to do that, but you can do it. All right. Now, if you go back to this, I've already erased all the text here. If I go back to, say, this reaction, and I look at which two substances look most like HBr, so that would be this one and this one. These two things differ by H+. It's really hard to talk and write at the same time. So the only difference between these two things that I've circled is H+. And so what we're going to do is we're going to call these conjugates. An acid-base conjugate is the pair of substances that differ only by H+. One will be the acid, it has the H+. One will be the base, it does not. Likewise, in this equation, the H2O and H3O plus here are also conjugates. I didn't write the S there. There we go. So an acid-base conjugate pair will exist in any acid-base reaction, and there will always be two pairs, because an acid must react with a base, and both of those things then switch their state from base to acid and vice versa. So you can then connect the two things together. So let's do some more examples of that. So over here, if I identify what my acids and bases are, so this is a base, this is an acid, this is a base, and this is an acid. What I would do is I would say, okay, what substance is NH3 but different by only H+? And that would be this. So these two are conjugates. The other two must also be conjugates. Now, importantly, when I say differs by H+, that could be added or removed. So you do have to look in both directions. So be careful about that. All right. How about for this one? So ignoring this text right here, I'm just going to cover up the text here. So All right. So hopefully you can't read the solution there, even though you could easily pause the video. There we go. What I want you to do is I want you to identify the acids and the bases. And then I want you to determine which ones are conjugates of each other. So write the reaction down for ammonia plus water. Write out all the products there that are on the screen. Label each as acid or base on both the reactant side and the product side. And then I want you to link the conjugates together by drawing a little curve like we were doing. So like linking two things together. All right, go ahead and do that. I'll give you about 2 or 3 minutes, and then we'll go over the answer. All right, one more. Ooh, excuse me. One more minute, we'll go over the answer. All right, so let me get the pen tool here. So if I look at ammonia and ammonium here, I can see that NH3 gained an H plus over the course of this reaction. So this must be the base. Looking at water, I can do the same thing. I can say, oh, it lost an H plus in doing that. So this must have donated it. That makes it the acid. And then I can do the same thing over here. Hydroxide gains H plus, making it a base. Ammonium gives up its H plus, that's the acid. And then I link the conjugates together. So I'm going to link ammonia to ammonium. Not in a box, but a trapezoid, I guess. There we go. And so I've linked the conjugate pairs together. And now we can get rid of all this highlighting so that we can read the font again, because it just basically says the answer. So there you go. All right. So that's going to be our task. Identify acids and bases, and then link the conjugate pairs together. All right. Here's a more ambiguous reaction because I'm not using ammonia or HCl anymore. We're going to use other acids. So I want you to do the same thing that you just did, and I'll give you 2 minutes to do it. So see you in a bit. All right, let's go over the answer here. Before Maya startles me again, she just did. Hi, Maya. She's on the floor now. All right, so I have H3PO4, which was 3 hydrogen, but after the reaction, it only has 2. So this must have given up an H+, so it's the acid. If it gave up an H+ to water, then water is the base. It's accepting it. Then we'll go to the other side, and here I have H3O+. To go in the reverse direction, it has to lose that H+, making it the acid. And thus, this must be the base. And then we just link the conjugate pairs together. Now, you'll notice that there's no real rhyme or reason to how I write these. I just sort of write whatever product in whatever order I want to when I'm creating these problems. So, it's not always going to hopscotch like this, where I go something and then skip and then its conjugate. So I might put the conjugates on the outsides, for example. Or you might just have 3 products, and there's something that's neutral and does nothing. So just be mindful of that. All right, so we can then do this, and I can hit clear so that you can see this text here, which is exactly what we labeled, so that's great. All right, one more to have you try. All right, let's go over the answers. So here we got water. And then looking over towards the right, we can see that water eventually becomes this. In order to do that, it must lose an H+. So that means water is acting as an acid here. That means that bicarbonate here must be the base, because it will accept the H+. Then on the other side, we have hydroxide, which is going to act as the base to accept an H+ to turn back into water. And that means that this must be the acid. And then we can link the conjugates together. So here's water. We're going to link it with hydroxide. And then we'll link the other two together. Whoop, there you go. Very good. All right, let me hit clear so I can do that. Now you'll notice that I'm writing the word conjugate on the right side here. You don't really need to do that, although for the purposes as written, this is correctly written. So if I have something that is an acid, this would be its conjugate base. But I could also say that this is my acid, and then this would be its conjugate base. So it's all a matter of perspective. But together they make what is called a conjugate pair. And that's really what I care about, is that you understand that. I do have more examples for you to try, but I'm going to leave these as an exercise for you to do on your own because it's more or less the same thing. It's very straightforward. Now, don't be alarmed when you see things that look weird. Like, what the hell is this thing? Well, it doesn't really matter what it is because what you can do is you could say, okay, let's look at it before and after. What must have happened? What did it act as? So I'm going to leave those as an exercise. We're going to go on to the next topic, which is where we're going to start doing math with this stuff. You might think, how the heck are we going to do math? Well, we could calculate concentrations of stuff, and that's what we're going to do. Now, because water is amphoteric, it can do this. I expected that. That's what I expected. So this process is called oops, that's the wrong color pen. This is called autoionization. Auto being the prefix that is used to represent self. Ionization meaning forming ions. So water can react with itself. Now, this is not very easy for water to do, so it doesn't happen all that often in the solution. Now, what I mean by that is it's not very frequent. It happens all the time because there are quintillions of water molecules in the solution. But of those quintillions, an incredibly small fraction of them react. And when they do, they act in this following manner, as shown on the screen here. Water plus water makes hydronium and hydroxide. Now, if I was to write the equilibrium expression for this reaction, I don't include liquids. I only include aqueous. And so I would get this, right? And because we know that the amount of H3O plus must be equal to the amount of hydroxide because it's the autoionization of water, those amounts must be equal in water. Now, for this expression, this reaction has an equilibrium constant of 1 times 10 to the minus 14 at 25 degrees Celsius. And because this is such a special circumstance that we have explicitly defined, we're going to give it a separate variable, Kw. Kw is the constant, the equilibrium constant, for the autoionization of water, and it is equal to this number, 1.0 times 10 to the minus 14. Now, if that's the case, then the square root of Kw must be equal to each of these, because if I say that H3O plus equals X and hydroxide equals X, then this number would equal X squared, and I could solve for X to be equal to this number. 1.0 times 10 to the minus 7 moles per liter. So to summarize how we came up with this, we were able to write the equilibrium expression for Kw. That's very straightforward. We know how to write those. We define Kw as 1 times 10 to the minus 14 at 25 degrees Celsius. And from there, we can then calculate how much hydronium or how much hydroxide is in the solution. And we get 1 times 10 to the minus 7 moles per liter for that. And so this all arises from this idea that water can auto-ionize on its own. And it totally does. And so these two slides will go through that. And there we go. Now, anything that has an H3O plus concentration equal to 1 times 10 to the minus 7 is what we call neutral. In order to be a neutral substance, you must have a hydronium concentration of 1 times 10 to the minus 7. If you have more acid than this, you are an acid. If you have less acid than that, you're a base. And the reason for that is because, remember that this expression must be true. So let me put that on the screen here. If Kw equals this product, and Kw is always 1 times 10 to the minus 14. Oh, I don't know why it's doing this, like, issue. I'm going to have to reboot my computer again after this. That's okay. Then 1 times 10 to the minus 7 is going to be the middle point, if these are equal. If I have more of this one, then I must have less of this one. Likewise, if I have more of this one, then I would have less of this one. So again, if I have this amount of H3O+, plus, I am neutral. Oops, you know what? I want to do it this way. I don't want to write it like that. And you'll know why in a second. So if I have more or less H3O plus than this number, then I define my substance as these terms. And for some reason, my pen is just freaking out here, even in Photoshop. All right. Now, because Kw is always this number at 25 degrees Celsius, multiplying these two things together must always equal Kw. And so we can calculate numerically what the amounts of H3O plus and OH minus would be. So let's suppose that we have an acidic solution where there is more than 1 times 10 to the minus 7 moles per liter of H3O plus. In this case, I have 1.0 times 10 to the minus 2 moles per liter. What would the concentration of hydroxide be in this solution? Try and calculate that for me. Should be pretty trivial. Type it in the chat. I'll give you a minute to do it. There you go. Very good. That's all you got to do. So we'll go over here. And so if I say, okay, well, Kw divided by H3O plus must be hydroxide. And so that would be just that, right? And when I divide, I subtract the exponents for powers of 10. And then we append the molarity unit afterward for our concentration. All right. So we're going to be doing calculations of this nature all throughout this chapter. This is going to be the whole point. We are going to want to find both the concentration of hydronium and of hydroxide for various reasons. One of those reasons is going to be a function that we're going to introduce in just a second here. All right. Let's do the same thing here. I have 0.001 molar sodium hydroxide. What is the concentration of H3O plus in there? I'll give you another minute to calculate that one. And then I believe we're due for a break. All right, let's calculate the answer here. So we'll go back over here to where there's nothing. There we go. All right, so I have a sodium hydroxide solution, which means that my hydroxide concentration is equal to 0.001 moles per liter. I wrote the wrong thing. There we go. So we're always working with this Kw expression up here. This one right here. And so since I want to solve for this one, I'll just divide both sides by the other thing. So that's what I'm doing down here. And there's my answer. So in a solution of 0.001 molar sodium hydroxide... Oh, oops, hold on, sig figs. There's my answer. I would get this concentration. Because, again, they have to multiply together to be 1 times 10 to the minus 14. And this will always be true as long as we're at 25 degrees Celsius. Which, guess what? All the examples we're going to do, 25 degrees Celsius. All right. So before we go on our break, let's do our summary here. A neutral solution will have this amount of H3O plus in it, 1 times 10 to the minus 7. And so there's my definition right there. An acidic solution will have more hydronium than hydroxide, and a basic solution will have less hydronium than hydroxide. And then finally, when you take the product of hydronium times hydroxide in an aqueous solution at 25 degrees Celsius, this must equal Kw, which equals 1 times 10 to the minus 14. So this will always, always, always be true. So commit this one to memory. This is worth knowing. H3O plus times OH minus equals KW equals 1 times 10 to the minus 14. We're going to take a break, which means we're going to be over here. Let me get the timer on the screen because I forgot to open it. I always do. And let's get the title track for Paradise Killer going because it is fantastic and I love it. Stay forever. There we go. Oh, hold on. It's playing for me, but it's not playing for you. All right. So there's our summary that we just went over at the right before the break. Let's apply that to some more examples here. So I want you to tell me, is this solution acidic, basic, or neutral based on the information presented on the screen? In a little bit, we're going to use a different rubric than looking at these numbers. But for now, I want you to just tell me, which state is it? Acidic, basic, or neutral? All right, I'm going to write my hint on here. I realize I'm working from the future and that you could be any number of minutes watching the video back. But remember that for all aqueous solutions, 1 times 10 to the minus 7 for H3O plus is neutral. All right, so let's go over the answer here. So you have it right. So if you have a number that's higher than that number down there at the bottom, then it must be acidic. So I have more acid than I would at the neutral point. So therefore, this must be acidic. Good. All right, how about this one? Is this acidic, basic, or neutral? Now, to solve this, we're going to do a calculation here. And so here's our calculation that we're going to do. Because we've been referring all of these to the amount of H3O+, but I gave you hydroxide, didn't I? So we're going to have to use the auto-ionization of water. So we got 1.0 times 10 to the minus 14 divided by this. And I don't know what the heck that's going to be in my calculator, so I got to punch that in manually. So divided by 6.35 times 10 to the minus 8. So I get this. I get 2 sig figs, as we're going to do. Well, actually, no, it's a definition, so I get 3. So 1.57 times 10 to the minus 7. I forgot my molarity. There we go. Okay. Now, this number is greater than 1.0 times 10 to the minus 7 moles per liter. So we would conclude that this solution was actually an acid. And that makes sense because the amount of hydroxide is less than 10 to the minus 7, right? It's only just slightly less, but it is less. And therefore, this must be an acidic solution as well. All right. So be careful because I think the trick here is that if people just start looking at the numbers, you're going to go, oh, duh, it's less than 10 to the minus 7. It's 10 to the minus 8. But, I could ask you for the other thing, and you never know which one I'm going to get, or which one I'm going to ask you. So just be careful about that. All right. So I want you to do the calculations here. I've given you only hydroxides. I want you to tell me the amount of H3O plus for each of these solutions, and then tell me acidic, basic, or neutral. So I'm going to number these for you. So this will be solution 1. This will be solution 2. And this will be solution 3. I'm going to give you 5 minutes. We'll go over the answers in just a moment. One more minute, we'll go over the answer. All right. So this first one, I mean, neutral, right? Because if it's got 1 times 10 to the minus 7 in OH, it's also got 1 times 10 to the minus 7 in H3O+. plus. These other ones, we have to actually calculate this, so we'll go over here to do that. Let me clear all this out, because we're kind of out of space here. All right, so KW equals 1 times 10 to the 14, minus 14, sorry, which is equal to H3O plus times OH minus. And we have OH minus for all of these, so we're just going to divide KW times OH minus, or divided by OH minus. That will give us our hydronium. And so for the second one, we have 1 times 10 to the minus 14 divided by 2.7 times 10 to the minus 1, which is going to give us a real small answer. So this one must be basic. 1 times 10 to the minus 2.7 times 10 to the minus 1. And I get 3.7 10 to the minus 14 molar. And this is super basic. And then for the third one, I wrote this in the wrong order. For the third one, we got KW over 5.9 times 10 to the negative 10. I don't know why I'm typing this in on the keyboard. 10. And I get 1.69. Okay, so 7 times 10 to the minus 5. And that's acidic. All right. Any questions, let me know. So now that we can calculate H3O plus and OH minus no problem from a bunch of different conditions, we're going to apply this to a new technique, and that's this. Everybody's heard of pH before. You do not need to take a Chem 163 class to know what pH generally is, right? It's that number scale. 7 is neutral, small numbers are acidic, and big numbers are basic. Now, more than that you might not know, and that's fine, because we're going to learn that. But almost everybody is familiar with this scale. It is a universally utilized scale for identifying acidic, basic, or neutral. Now, you might not know the nuance of this. The pH scale is a log scale. Now, this is not natural log, this is base 10 log, so we're going to need to hit a different button on the calculator. That's this button right here. So we were using ln earlier for, like, say, delta G equals RT ln K, We're going to need the log button now for that, for pH. So make sure that you have the correct button. Very, very, very crucial. If you are using Wolfram Alpha, it thinks typing in the letters LOG is natural log. So on Wolfram Alpha, let's get Wolfram Alpha up here. If it'll load. There we go. So if I do this on Wolfram Alpha, and this is super frustrating, and it's kind of the only thing I hate about Wolfram Alpha. Because who does this? If you type in this into Wolfram Alpha, log of 10, it's going to give you this number, 2.3, whatever. But if I type in 10 and I hit log, I'm going to get 1, which is the correct answer, right? So what you have to do on Wolfram Alpha is whenever you're doing log and you mean for it to be base 10, you have to actually type log 10. And then it will know, oh, you actually meant log 10. Oops, I don't know why it corrected that to log 1. I want log 10 of 10. There we go. And then I should get 1 as the answer. And I did, and you just can't see it because I got to make it bigger. So if you are using Wolfram Alpha for a calculator for any reason, please be mindful of that because it interprets regular old log as ln. In fact, if I just do ln and I do that, it'll give me the same number as me typing in just log. So that's the only issue that I have with Wolfram Alpha. If you are using it in this class because you don't have a calculator handy, just be mindful of that. All right. The formula for pH is going to be this formula. Negative log base 10 of whatever your concentration of H3O plus is in moles per liter. We drop the units because for the same reason as we do it for K, we divide by a reference, which is a 1 molar solution. So the units drop out. Now, note that this is H3O plus to find pH. There is another formula later on where we can do the pOH. Now, how do you do sig figs with logs? A log function is a different function than addition, multiplication, addition, subtraction, or multiplication, division. Those all have their own rules, right? When I multiply or divide, I have to take the number of sig figs from the figure that has the lowest sig figs, or the smallest number of sig figs. When I do addition and subtraction, I do places, right? The way that we do sig figs with logs is that when you take the log of something, however many sig figs are in this number that you input will be the number of decimal places that are kept. And you'll see this as I do examples. Now, we're at 163. I'm not super strict on sig figs, especially with logs, because, surprise, you probably didn't expect to get a new sig figs rule today. I just don't really care enough about it. You're going to punch in a number in the calculator, and I'm going to do it right because I have these rules ingrained in my head from teaching this stuff. But if you keep too few digits or too many digits or whatever for your pH, I don't care. It doesn't matter. I just want you to be close. All right, let's do some examples. What is the pH of this solution? Well, if pH is negative log of H3O plus, we could just punch this in the calculator. 1 times 10 to the minus 3 log, and then negate. So this would be pH 3. Specifically, since I had 2 sig figs in there, I'm going to put 2 decimal places. All right, now you try it. What's the pH of this? Oh, I gave you hydroxide. So what do you got to do before you do this? You can't just negative log this number, because it's not HP3O+, right? So guess what you get to do? You get to break out KW. All right, go ahead and calculate the pH of the solution. And I'll give you a hint, you should get an integer. One more minute to calculate the pH. All right, so if we do our calculation, oops, I can't see this because I put it behind a screen. Not H3O+, I have hydroxide. What am I doing? So if we do our calculation, I get that. And when I punch that into my calculator for my pH, that would be that. And you could probably guess that we're going to get 8 out of this. So 1 times 10 to the minus 8 log negate. And there you go. All right. So that's how we calculate pH. Very straightforward. We're going to do that a lot. In a lot of the problems that we're going to be doing coming up in this class, the trick is going to be getting to this point. What is this number? And we're going to be answering crazy equilibrium problems to try and figure that out. Now, if you have a solution with H3O plus equals to 1 times 10 to the minus 7, the solution is neutral. We defined that. Therefore, if we take negative log of that number, you will get 7. 7 is the midpoint of our pH scale. Anything that's pH 7 is neutral. At 25 degrees Celsius, if you have a solution with pH less than 7, you are acidic. If you have a solution with pH greater than 7, you are basic. If you are on 7, you are neutral. Now, at different temperatures, these numbers do shift around a little bit because remember that equilibrium constants change based on concentrations and temperature. The autoionization of water is endothermic. You have to heat it up to get water to react more. So K will change as temperature changes, and that's going to change the amount of H3O plus that is our definition of neutral. Now, for simplicity's sake, we're going to do all of these problems at 25 degrees Celsius because calculating a new KW every time is really obnoxious. You can do that in 300 level chem when we do analytical, but for our purposes here, we're going to stick with just 25 degrees Celsius. On the bottom here, I have a scale of potential pHs and then the concentration of H plus in moles per liter that is assigned to that. And you can see that it's basically 10 to the minus pH, right? So the amount of H3O plus that's in there is 10 to the minus pH moles per liter. And so that's neat and interesting, because now if we have just a regular pH, like 7.2, I know that H plus would be 10 to the minus 7.2, whatever that ends up being, and you could type that in your calculator. So if I do 10 to the, oops, hold on, let's do it this way. So I do minus 7.2, 10 to that would be the concentration of H3O plus in such a solution. So that's helpful to know. So keep that one in mind. On the screen, I have a list of just various substances and their pH. You'll notice that in the middle here, so here's pH 7. Things that are relatively close to this line are pretty inert, and they're pretty safe. For example, coming into contact with unpolluted rainwater, not very hazardous. You know what's more hazardous? Cherries. Cherries are much more hazardous than rainwater, right? Because you might eat them and choke on the pits because they're so good, and I just want to eat cherries. As we deviate farther away from pH 7, we get to substances that are more and more dangerous to not just our physiology, but for like just parts of your body. For example, if you consume too many soft drinks, which have a very low pH, this isn't necessarily hazardous to your body, but it can be hazardous to your teeth, because your teeth are made of a compound that has hydroxide in it, and the hydroxide will react with the acidity in the soft drink, which is obviously no good because you want to have your teeth. So you can develop cavities and rot your teeth away by consuming too many things that are acidic. And it's not just soft drinks. So if your parents told you, don't drink soft drinks, you're rotting your teeth, and then they let you drink like orange juice or something like that, it's just as bad. So it's not just soft drinks, it's anything that has acid in it. And that includes lemons and limes. I love lemon and lime. I'm drinking lime polar seltzer right now, which is not going to be pH 2, but it could be hazardous to certain things in your body, for example, your teeth. Now, if you go past pH 1, that can be hazardous to everything, really. So pH 1 is the pH of your stomach acid. Your stomach is roughly 0.1 molar HCl. Depending on what you have eaten or your health, or if you have acid reflux or something, those numbers vary wildly. Going in the other direction down here, if you are further away from pH 7 in the... Where's my cursor? There's my cursor. In this direction, in the basic direction, you actually rather quickly reach things that are not super great for you. So, for instance, milk of magnesia, which is used as a sort of neutralization for stomach acid so that you can recover from like a stomach ache or something like that. pH 10.5. Much further beyond that, though, you get into the dangerous territory. For instance, oven cleaner and lye and stuff like that are pH 14. These are things that will dissolve your flesh, not generally desirable. Our body tends to handle acids a little bit better than bases. The reason being, the first thing that anything hits in your body is the stomach, if you consume stuff. That being said, your blood is very, very, very pH intensive. Like, the pH of your blood must remain around a very specific pH range. If you go very far past 7.3 or 7.4, you die very quickly. I think 6.8 or 7.8 is fatal. Now, we're going to learn in this chapter that there are various methods by which we can protect a pH range, which is very fortunate because otherwise one drop of soft drink would be enough to kill a person if you didn't have a buffer in your body to resist pH changes. But anyway, those are just some pH ranges that are available for various substances. All right. Now, we have already done questions like this. You were able to look at this number and go, oh, hey, it's greater than 1 times 10 to the minus 7 in H3O+. It must be an acid. Well, now you could calculate the pH. And so let's check that this is the number that I get here. So 2.6 times 10 to the negative 3. And we're going to log 10 it. And then we're going to negate that. Negative 2.585. So 2 decimal places would be 2.59. So there's my pH. All right. Easy enough. So calculating the pH is pretty straightforward. Now, I'm going to cheat really quickly. I kind of want to talk about POH. I just don't know when that's introduced. 2 slides away. Okay. We'll get to that in a second then. So same thing here. If I wanted to calculate the pH of this solution, I would need to know H3O+. So let's do that real quick. So 1 times 10 to the minus 14 divided by 8.3 times 10 to the minus 6. This would be H3O+. We're going to log that, and then we're going to negate it. So this pH would be 8.92. And that would be basic. All right. What do you do if you have to go to the other direction, though? What if I gave you a pH, and I told you, tell me how much acid's in there? Well, let's go over here. We'll put this on the screen. So how do we undo this process? So if the pH of something is negative log base 10 of how much acid is in there. So the first thing I can do is I can move this minus over. So I could just do this. And then I have to undo log. You'll notice that I've been writing this 10 here the entire time, and there's a reason for that. The opposite function of log base 10 is 10 to the power of. So if I do 10 to the minus pH equals 10 to the minus, or I'm sorry, 10 to the log base 10 of H3O+, this function and this 10 cancel each other out. So this formula tells you the amount of H3O+ in a solution. And we actually said this earlier, didn't we? I said 10 to the minus pH is how much acid you have, and this is just the mathematical proof of that. So, if I have pH 4.90, then the amount of acid that's in there will be 10 to the minus 4.90. So, we'll punch that in. And I got 1.258. Well, okay, hold on. So after I did pH, I had 2 decimal places, so I get 2 sig figs. So 1.3 times 10 to the minus 5 moles per liter. So that'd be the concentration of my acid there. And lo and behold, that's exactly what we got. All right, let's have you try this. I have a solution that's pH 9.05. What's the concentration of hydroxide? Ha ha ha, you have to play with KW. I like that I get to do all the easy examples, and then you have to do the KW nonsense. So, go ahead and solve this. I'll give you about 3 minutes, I think is probably appropriate. So, we'll check back at that. All right, 1 more minute. All right, let's calculate the answer here. That's the wrong problem. I want this one. There we go. All right, so I have pH 9.05. So that means that if I calculate H3O plus, that must be 10 to the minus pH, which would be 10 to the minus 9.05, or, so 9.05 negative 10 to that, which is equal to 8.9 times 10 to the 10, or 10 to the minus 10 moles per liter. So that's how much H3O plus is in there. And then we could say, okay, well then Kw equals H3O plus and OH minus. So we'll do Kw over H3O plus equals OH minus. And that would be 1 times 10 to the minus 14 divided by this number that I just calculated. So I'm just gonna do this times 1 times 10 to the minus 14, just to get the answer out there real quick. And when you do this calculation, you should get this. And if you're wondering what I did on the calculator, I had 8.9 times 10 to the minus 10 in there, so I hit inverse. So I was taking 1 divided by that number times Kw, which is essentially what I did here. So there you go. All right. I have a bunch of practice problems here that I'm going to skip over because I only have 3 minutes left. I just want to talk about indicators and POH real quick in the last few minutes of the class so that we can end on like a nice spot because there's only a few slides. Excuse me, a few slides left. All right. So what is POH? POH is the same thing as pH with OH. So you just take minus log of OH to get the POH. Now, why do we do this? The reason that we do this is because there's a second handy formula, and that's this. If I add the pH and the POH together of a substance, I will get 14. And the reason that you get this is because this arises from the Kw expression. Kw is 10 to the minus 14. Here's the H3O plus part. Here's the OH minus part. I can prove that to you, but it would take me more than 3 minutes, and I got to play with logs. And let's just not bother. Just assume that it's true. You can look up the proof on Wikipedia if you'd like. But it is derived from Kw. Now, what this means is that if it's easier for you to do this process, for example, we've been doing all this Kw nonsense. Whenever we have to deal with OH, we just figure out what H3O plus is and then throw it in Kw. Now, if I'm given OH minus, I could just find the POH and then do this, and that might be easier for an application. So, for example, if this is my H3O plus concentration, and I'm asked, what's the POH? You might say to yourself, oh, I need to use Kw to figure out what OH is and then subtract. Or I could find what the pH is, which would just be this. So 5.5 times 10 to the negative 2. We're going to log that and negate it. So that's 1.259, so 1.26. And then I'll just say, okay, well, pH plus POH equals 14. So I'll just do 14 minus this number. That's not 14. That's... There you go. And so there you go. So this will save you having to use Kw. In my experience, both expressions are pretty straightforward. They don't take much time to use. It's really a matter of preference. But it's another tool that's here and available for you if you would like. Last thing I want to talk about today, since we're out of time, but I'm going to talk about the indicators anyway. So what is an indicator? An indicator is a tool that is used in the laboratory to tell you what the pH of something is. Now, we're going to talk about pH probes later. We're going to use a pH probe in lab number 3. So not this Friday, but the next Friday, we're going to do an acid identification lab where you get to play with all the lab instrumentation including the stuff in the back room that you guys all went and looked at and were like, oh, this is boring. I assume, anyway. So we're going to use pH probes for that, but for a lot of the labs in this class, what we're going to use is called an indicator. An indicator is just a substance that has one specific color or pigmentation to it below a pH, and then when you go above that pH, it turns a different color entirely. In the middle neutral part, there may be an in-between color. So for example, bromothymol blue is very, very green at neutral pH. As an acid, or if the solution is acidic, it turns yellow, and if the solution is basic, it turns blue. I have a picture right here of a weak acid being titrated. You can see that this solution is colorless during the acid part. It is very pink during the base part, and then it is faint pink in the middle. You have used phenolphthalein in many labs in this quarter, and we've said, like, oh, not this quarter, but in this course, so Chem 160, whatever. For instance, in Chem 140, we had you do a sulfuric acid and sodium hydroxide titration, or a vinegar and sodium hydroxide titration, and you titrated to a faint pink, where faint pink was the end point, because it was in the middle of the pH scale, around pH 7. So that is something that we commonly use. But any indicator can be used for any process that you really need to. Here are some examples of different indications. So methyl red turns red around pH 5 or so. Above pH 5, it is yellow. Here's just a giant chart. Of a bunch of different indicators here, and their colors. So where they change. So for example, if I had something that I was monitoring for pH and I wanted to be very sure that I knew when it hit pH 4, I would pick this indicator probably right here, bromophenol blue, and then I would say, okay, if it's blue, it's above pH 4. If it's yellow, it's below pH 4. If I wanted pH 8, here's probably my best choice here, M-nitrophenol. If it's below pH 8, it's red. If it's above pH 8, it's orange. And you could do that with any indicator you want to. Some indicators are even good for multiple pHs. Something you'll notice is that all of these substances have names that sound like they are things out of when Bob Ross would like list off all the paints that he would use, like alizarin red, or let's see here. I don't know. I was thinking bromothymol, but I don't know if that's one of the things that he did. But like that's actually where a lot of these colors come from, is that they're used in pigments that we use in paint. So just a little Bob Ross to end your day there. All right, that's all we're doing. We'll come back to talk about strengths of acids and bases next time. I do want to thank everyone for coming to the lecture. Remember that we do have lab on Friday. Please don't be late. I'll try to be more on time and not have issues with a printer that I won't need to use. So we'll start at 9. And again, I don't care if you stay late. Like, all I do is go to Taco Book after anyway. So whenever I get lunch, that's fine. What else do we have? Yeah, the quiz for Chapter 13 and Lab Worksheet number 1 are all due Friday. Make sure you don't let those sit. You don't want to push those off till Thursday night. Do the best you can on those. Ask me any questions in Discord or email. See you on Friday.